Hello. Welcome to second video of energy production. Today we're going to be going a bit in depth on how exactly energy is produced inside plants like nuclear plants, how solar energy is produced, and things like that. And it's really vital that you understand the in depths of this because in IB exams, especially the FRQ parts or paper two, you're going to have questions like explain the role of a moderator in a nuclear reactor and or explain the disadvantages of fossil fuel energy. So pay attention. Now, let's take a look at how a fossil fuel plant works. Fossil fuel plant uses fossil fuels, of course, such as let's take coal as an example. Now, let the coal is heated up in a boiler. This is the boiler. And water from a river, for example, is sent through pipes and the boiler heats up this water. Now, when you heat up that water, it generates high pressure steam which goes through a turbine and it rotates that turbine. Now this turbine rotates the coil of a generator which creates electricity through electromagnetic induction. After the steam is sent through the turbines, it is condensed to water again uh, with the condenser, so that turns it into liquid water so that this can be reused. So a nuclear reactor generates nuclear energy through nuclear fissions. If you recall fissions from our last unit, it's basically a nucleus splits into multiple nuclei while releasing energy and more neutrons to initiate another chain reaction. And this turns into a chain reaction as you can see here. And so this is why it's self-sustaining. It lasts for a really long time as you start with a small quantity of uranium 235 and that produces an immense amount of energy. Just to get an idea of how much energy it produces, if you eat 1 gram of uranium 235, you're going to gain 20 million calories. And also you'll get diarrhea and then your lungs start to fail and then bad things happen. So don't eat uranium. However, you're gonna have to have a minimum mass of uranium 235 for this chain reaction to occur. Then that's called the critical mass. And for a pure sample of uranium 235, you're gonna need 15 kilograms of critical mass. And however, you're not gonna have pure samples of uranium 235 generally. As you mine rocks, a rock may have, say, 10% of uranium 235 in it. 15 kilograms of rocks will not suffice if it only has 10% of uranium 235 in it. Now, let's take a look at how a typical nuclear reactor works. Inside the nuclear reactor pressure vessel, you're going to have fuel rods, the gray thing over here, which contains our uranium. A moderator is a substance, most typically it's either granite or water used in nuclear reactors, that control the speed of the neutrons so that they can initiate reactions. Neutrons are just way too fast, and sometimes they just need to be slowed down to initiate reactions. And the neutrons in the fuel rods transfer thermal energy into water, which heats up and produces steam. And now the heat exchanger extracts heat from the moderator, and this goes into the turbine to generate electricity. However, that is not all. We also need to have safety measures in place. There's these things called the control rod, which absorbs neutrons to decrease the rate of the reaction. Sometimes the chain reaction can get a little out of hand, and we need control rods to do that. Now, the control rods operate up and down. You can send them up through the fuel rods to control the reaction, um, and you can send them down when you want to increase the rate of the reaction. And now, if you do not properly control the rate of your reaction, what happens?
There has been a nuclear accident in the Soviet Union, and the Soviets have admitted that it happened. The Soviet version is this. One of the atomic reactors at the Chernobyl.
So there are two main types of fission reactors: a pressurized water reactor, the one we just looked at, and a gas-cooled reactor. The main difference is that you have your water as the moderator in a pressurized water reactor, and in a gas reactor you have graphite generally as a moderator and gas as your coolant. Now, the sun is an excellent source of power. Thank you very much, sun. Do you have anything to say to that? Oh well, on a clear and sunny day, the Earth will receive about 1,000 watts of power per 1 meter. 1,000 watts per 1 meter, and 1,000 watts is basically 1,000 joules per second. So every second on 1 square meter of land, we're going to receive 1,000 joules of power. And we harvest solar power through solar panels and photovoltaic cells. They're two different things actually. They're similar but a little different. Here we have solar panels, and it collects the radiation from the sun and it turns it into heat. And so it's used for water heating or air heating in the house, but it does not convert it into electricity. Now, the panels are installed above um, the water pipes here, and so the incoming radiation from the sun will heat up the water which goes into our house. Let's A photovoltaic cell, whereas it takes photons from the sunlight and turns that directly into electricity. Today, PV cells have an average efficiency of 30%, which means that they're able to convert 30% of the energy from photons into electricity. Now, sunlight incident of the cell, it releases electrons which establish that potential difference across the cell. And both the solar panels and photovoltaic cells are coated with a non-reflective surface to improve efficiency. We don't want sunlight to reflect. That can decrease how much heat or photons we absorb. Okay, now hydroelectric power. This is one of the most established power source, and here's how it works. You have a dam, for example, which releases water, and the water always flows downhill. And so as it flows downhill, it gains kinetic energy. The water has potential energy at one height, and it gains kinetic energy as it goes downhill. And this kinetic energy is utilized by the turbine to generate electricity. Now let's do a little derivation on how this works out. Okay, so we want to convert potential energy to kinetic energy for a water that falls a height h with the velocity v. Now kinetic energy is equal to our potential energy. So Ke is mgh. Now recall that density equals mass divided by volume. So mass is density times volume. But the volume actually does not stay constant. Water may occupy a different volume down here than in here. So really, this should be written as m equals rho delta v. So Ke equals rho. That's a very bad rho, but oh well. G delta V G H. That's the kinetic energy. Now, if we want to find out power is, remember, um, energy times time. So we're going to look at how much time it takes for water to fall down from here to here. Now, this becomes P equals K. Oops, hold on. P equals rho delta V G H divided by delta T. That's your power. However, we can actually write delta V by delta T as Q. This is how it's represented. Q is the volume flow rate. So uh, it's the amount of volume that flows per over a period of time. So finally, we get P as rho Q G H. That is measured in watts or joules per second. That's your P. However, dams are usually installed on rivers because a river always flows. You're always gonna have water. If you're on a lake, for example, where's all you install you dig the ground and you install a dam, and then you're just going to use up all the water from that lake and you're going to flood the whole area. So that's not really good, is it? So we're going to use something called a pumped storage system, in which basically water is pumped back between two reservoirs, and so water is reused. And wind power take advantage of kinetic energy of the air rather than water.
Stop trying to take advantage of me.
Their average efficiency is also about 30%. And let's do a quick derivation on how this power is generated. Alright, so let's say we have a windmill. I'm very good at drawing windmills, ain't I? And kind of like the windmills with its radius r to wherever it extends, That's how much air that it's going to capture. And it's like a cylinder when you consider it through a function of time. So this cylinder is going to pass through the wind so that the turbines can uh, utilize the wind. So we're going to have kinetic energy is 1/2 mv squared. Now recall that mm, uh, density is mass divided by volume, and so mass becomes PV, sorry, rho V. So KE is 1/2 rho V, big V, little v squared. This is volume, by the way, just so you know. And volume, like, this is going to be the cross sectional area, and this is going to be the length, the total length of some blob of air with its cylindrical cross section that's going to go through the turbines. So now volume is going to be area times the length because it's in 3 dimensions. This is 2 dimensions and this is one more. So now KE equals 1/2 rho A L V squared. Now recall that velocity is distance by time, and now this distance is really just L. So we can write velocity as L by time because we're going to analyze how much time it takes for a wind with the speed of V to go through this. So now we have L equals V times T. So K E equals 1/2 rho A V TV squared. So now that's literally just 1/2 rho A T V cubed. That is your kinetic energy, the kinetic energy that the wind turbine will harness. But remember, this assumes that the wind turbine has 100% efficiency. So this kind of just counts as your input energy. That's not all. So there's this thing called wake effect. You see all these wind turbines lined up. If this turbine, for example, receives an airspeed of 100 meters per second, since this wind turbine is directly behind this wind turbine, the this wind turbine already slows down the air, and as you can see, velocity is directly proportional to power. So that means that this wind turbine will not generate as much power as this one does, and this wind turbine back over here generates even way less power than this turbine or and this turbine. That is called the wake effect. Alright guys, so let's take a look at the pro and con table. I'm not going to go through the whole thing, but you see, for solar energy, hydroelectric energy, and wind energy, they're kind of free. I mean, I say free because there are still maintenance costs and whatnot. But it's not like nuclear energy and fossil fuel energy where you're gonna have to extract the fuel from somewhere and then send it to a plant. Um, Now, one disadvantage of fossil fuel energy is that it is the most polluting energy of all these five types of energy. It's really bad for the environment, even though it's relatively cheap. And nuclear energy, as I showed you, Chernobyl can happen. And this is actually in our textbook. I'm not putting this down there to be too funny, but a disadvantage, and this is acceptable in an FRQ answer, is that someone will be tempted to make nuclear weapons. And even for this, wind energy. Now, I personally think that wind turbines are just beautiful, but some people don't. And people don't like the look of wind tunnels in parks. All right, guys. Well. Thank you very much for joining me today. Tomorrow, I'll release the last video for energy production, which will be focused on thermal expansion. Bye bye.